Okay. Here are the definitions of the I, J, and K vectors. In R3, I is 1, 0, 0, J is 0, 1, 0, K is 0, 0, 1. Here's the picture. Okay? That should be obvious. But if you haven't thought about three-dimensional coordinate systems, you might have to think about it a little. Of course, you have your textbook. It'll explain things. In R2, I is just 1, 0, J is 0, 1, and K doesn't exist. It's outside the plane. Okay? An example of how I might use this, V equals two negative 3, 5 can be written as 2I minus, not plus, 3J plus 5K. Okay, well, you know what? 2I would be 2 I's, okay? And negative 3J would be in the direction opposite to J, 3 of these. So you'd have to come out to here and out to here, and you have a point in the plane about here. But then you have plus 5K, which is 5 of these up here. So, let's see. You come out negative 3J, 2I, and then 5K. So 5 of these would be 1, 2, 3, 4, 5. Okay? You depict it like this, where this is, use a different color here. Here's 3 J's in the opposite direction, right? And here is an I and a second I. So this is 2I, which gets you to this point in the XY plane. And then here you have 5K. This is a little bigger than these, but they're probably the same. Okay? That's a handy picture to understand. Now, there are other ways to draw it. You can see it in your book. And I do recommend that you sketch a lot of these, because it reinforces all kinds of properties in 3 dimensions. Okay. Now, that is the IJK representation of any vector from R3. Very simple correspondence. Okay, cross product. I cross J equals negative K. And J cross I equals K, because if you reverse the order, you get the opposite, or the negative, of the result. That's true for all vectors. But we can, by defining it in terms of just what happens to I and J, we can figure out the properties of the cross product, all the properties. So that's what I'm going to define it. Okay, I cross K equals J, and of course then K cross I equals negative J. And J cross K equals I, so that K cross J equals negative I. Now, without doing a numerical example, subscripts of these coefficients. So P is A1I plus B1J plus C1K. W is A2I plus B2J plus C2K. Then B cross W is this. Not obviously, because if B is this, W is this, well, here's B and here's W and here's a cross. That equals A1I cross A2I plus B2K plus C2K plus B1J times cross A2I plus B2J plus C2K. Now what am I using here? What property am I using? Property in algebra. Learned it a long time ago. Got a name. Distributive law. Now, I am asserting that the distributive law works for vectors, for the cross product, because this isn't just plain old multiplication. But it turns out that it works, and we can prove it rigorously. Your book might or might not do that. I don't remember. Okay? I know it's proved rigorously in linear algebra. Maybe just asserted, certainly in physics, and in this course, depends on your textbook. Okay, so anyhow, and then we do plus C1K cross A2I plus B2J plus C2K. And of course we can apply the distributive law again. A1I cross A2I. Oh yeah. And there are three more important properties here. Now, the cross product is a vector. I cross I is the zero vector, meaning it has every component equal to zero. Okay? So anyhow, we have A2I cross A2I, A1I plus A1I plus B2J plus A1I plus C2K plus B1J I wrote some pluses where I got crosses. B1J cross A1I plus, etc. The pattern should be clear. We're just distributing this through here and distributing this through here. Well, this equals then A1 times A2 times I cross I plus A1 B2 times I cross J, and so forth. In other words, when I do A1I cross A2I, it's just A1 times A2. Those are just the numbers. So just like in multiplication, they can factor out. Leaving me I cross I. And here you have A1I cross B2J. Well, the A1 and A2 factor out, essentially. And you end up with I cross J. Okay? Make that J look a little more like a J. If it's a better dot. Okay. So that's all we're saying here. Now, you can write this out. You're going to have, what, 9 terms. Okay? 3 of them will be 0 because I cross I is 0. You're going to get a J cross J. If you write everything out, that'll be 0. K cross K will give you the 0 vector. Okay? That'll leave you 6 terms. Okay, well that's how we define the cross product. It turns out that there's a easier way than the distributive law to calculate a cross product, although the distributive law is actually simpler if you've got a lot of the components of your vectors are 0. Okay? So that okay, well, first of all, there are a couple of properties, and I'll tell you an easier way to calculate it. V cross W has a magnitude that's equal to the magnitude of V times the magnitude of W times the sine of theta, where theta is the angle between. And in 3 dimensions, that can be visualized very specifically. Also, V cross W is perpendicular to both V and W. Okay? So if I've got a vector V in this direction and a vector W in this direction, well, there's some angle between them, right? This is a fairly small angle. The sine of theta is pretty small. Okay? The closer the vectors get to being in the same direction, the closer sine of theta gets to 0. The closer the two vectors get to perpendicular, the closer the sine of theta gets to 1. Okay? Except, of course, well, we won't worry about that. Okay. And actually, I should have absolute value signs around the sine of theta, because the magnitude can't be negative. The sine of, and theta might be negative the way you measure it. It usually won't happen because it's usually just the angle between, not any directed angle. But okay, just be careful. We'll do that. Okay, so V cross W is perpendicular to both of these. Now, what's perpendicular to this and this? Well, either that or that. Which one is it? Yeah.